All right, so you've designed a sweet glider, and now you're ready to enter this glider in the competition. I'm just going to walk through the steps of everything you need to do after you've designed this glider, everything you need to be able to submit for it to be run in the simulator. Okay, so this is the baseline glider, and that I've got an example of, and you've worked through it and probably know where a lot of this design comes from at this point, but it doesn't matter what your glider looks like. We're just going to walk through what you need to do to now submit this for the competition. Okay, so for the first step is to make sure that all of the information in mockup here matches what you have over here in the in your inertia calculator. Okay, so this is that mass and inertia spreadsheet that's doing all of the mass calculations for where the center of gravity is and what the inertias are of the aircraft. And so you want to make sure these two things are identical. So let's just go through and double check it. Okay, so let's go through each of the components. So we'll start with the main wing. So the main wing has a semi-span of 4.5, mounting angle of 4.8. Actually, that doesn't matter for the inertia calculator. Dihedral of 13.7. So let's just go over here to the main wing. And remember, everything in green basically is what you need to check over here. This is all the editable stuff. So here's my main wing. I have a left and a right side that I've entered. We have to enter those separately on this mass spreadsheet. Each of them have a mean chord of 0.75, a semi-span of 4.5, airfoil thickness of 0.12, and then the wing root location is at 0. We can double check that over here in object. See, this is at 0, 0, 0. This is the X, Y, and Z location of that wing. And and actually these three slots here are the X, Y, and Z locations of that wing. So for us it's 0, 0, 0. And then the only other thing we need to input is the dihedral, which again is 13.7. So that matches. Okay, so we've got dihedral on the main wing. So now let's check our horizontal stabilizer. And so let's see, that's got a semi-span of 1 and root and tip chord of 0.75. So that's our horizontal stabilizer down here. We've got a left and a right side, each at 0.75, mean chord, semi-span of 1. Airfoil thickness, again, 12%. And then the location, we need to double check the location. So I've got minus 1.9492. So that checks out for both. And again, we have the left and the right-hand side, right? And then the dihedral is 0. So I've left those blank. You can put in a 0 if you like. And remember, these are X, Y, and Z locations, right? So if this wing is somewhere outboard, then Y would have a non-zero value, and then of course Z, if it's offset vertically from the origin, then it would have a Z value there. But mine doesn't. It just lies here right on the X-axis, and so that's why it only has an X value. Okay, so then let's look at the vertical stabilizer. That's our last thing to check here, the last lifting surface. So here's the lifting surface there. And the geometry has a semi-span of 1, a dihedral of 90 degrees, and a chord of 0.75. So on the vertical stabilizer, you just choose left or right, at least for this design, right? So I've just chosen right here. It wouldn't matter. Mean chord of 0.75, a semi-span of 1, 12% airfoil thickness, and then let's check our location. So it says minus 2.4489. So there's minus 2.4489. And then the last thing here is the dihedral, and it's at 90 degrees. And again, I don't have any vertical or Y or Z offset of that lifting surface, which you could have, but I don't. Okay, so we have all of our lifting surfaces in there correctly. Now let's check. We've got these other two things that we need to make sure match up. So the carbon fiber tube and the tungsten ballast. So I'm going to come back over here and look at, so cylinder 4 for me, and I could have, let's just rename that right now. So that's the carbon fiber, and let's see, it has a position of minus 0.3415. So let's check that first. So here's carbon fiber, minus 0.3415, so that's in the correct location. And then its geometry, it's got a height. That's what we call it. In mockup, it's called a height. That's the length of the tube, and that's 6. And so, yeah, the length of 6 feet. So I've got the location, and again, mine is not offset from the center line, so it only has an X value. And then we actually can't choose the outer and inner diameter. That was specified in the problem statement, so we can't change those, and that's why those are in gray. And let's see, those should, let's see, the outer diameter. Oh yeah, so this is an outer diameter 0.0625, which means that the outer radius here is 0.0313. So so we're just looking at the outer surface of that cylinder. Okay, so that looks like it's set up correctly. And then let's check this last thing. This is our tungsten ballast. I'll rename that. Okay, so there's our tungsten ballast, and it's at location 0.7150. So let's make sure that matches 0.7150, 00 there. And on this one, we can choose a length and an outer diameter. So let's come over here to the height is our length, so that's 0.0417. That's correct there, 0.0417. And this is repeating because I put in 1/2 divided by 12 because we're saying it has a length of a 1/2 inch. So when you convert that to feet, then it's 0.04166667, but I just put in 0.0417 over here. And then the outer diameter, and of course this is asking for it in the radius of this, so this should be half of it, but the outer diameter was 1.5 inches, and when we change that to feet, it's 1.5 divided by 12, so we get 0.125 there. And when we get change that to now a radius instead of a diameter, we divide it in half again, so we've got 0.0625 over here. Okay, so that's the radius at the top and bottom, and that's our tungsten ballast sitting right there. Okay, so that's just our weight that's helping our CG get in the right location. Okay, so now, speaking of CG, we need to now check our center of gravity location, and I believe I've updated my I think I've made some changes here, so this may not match exactly, so I need to update it. So so this is my true CG location from the mass spreadsheet. So now we need to make sure that that matches what is in here, and of course we can't edit it over here. This is a result. It's the locations of all these wings and ballasts and everything are producing this CG location, and now we need to copy that CG location into mockup to make sure that it's giving us the correct aerodynamic information. Okay, so let's check our center of gravity. So that is the location. Again, this is X, Y, and Z, and these are X, Y, and Z here. So so yeah, my CG is off a little bit, so I need to type that in. So minus 0.0267. That should be accurate enough. And then Y is 0, and then Z, I've got minus 0.1790. Okay, so that corrects our center of gravity location. So that's this red dot right there. You can see where that's sitting here. So now my center of gravity over here matches the center of gravity that I have right here. Okay, so at this point, I'm done checking between mockup and this mass spreadsheet to make sure that everything matches. And we have to make sure everything matches, or we're going to get an unrealistic design. Okay, so everything checks out between these two things. And now I'm ready to start filling out the file that will be used in the simulator. Okay, so let's just walk through this file. This is a JSON object. You can see up here I've called it 0000.json. JSON is simply a text file. The last 4 letters here just say it's an extension called a JSON, and but it's really just a text file of human readable information inside of it, and it's got these brackets that basically organize the information within the text file. Okay. So we're just going to go through and check all this stuff, and you can download a copy of this. So you have access to this, you download a copy of it, and then you just need to go through and fill out the information for your particular glider, okay? So I called this baseline glider. Of course, you can call your glider whatever you want. This is just a name that you're gonna call it. And then it's asking for a wing area. Okay, so this should be the area of your main wing. Now, if you have this set up correctly where wing 1 for me is my main wing, and in geometry I selected main wing there. And then for the horizontal and the vertical, notice that that checkbox is not selected. So those are not part of the main wing area. And so when you go to analysis, anytime you update anything over here, it's going to tell you what the reference area is. That's your main wing area. So 6.75 is my main wing area. So that's what I've got here, 6.75. And then the main wing span for me is 9. And that's 2 times the semi-span. My semi-span of the main wing is 4.5, as you can see right here. So that's just 1/2 of the wing. And so the total span of the wing is actually 9. Okay, so now let's see, what's our operating weight right here? So this is the weight of the aircraft. So that we're actually going to get from this spreadsheet here. We have the mass, that's the total mass right there. And so you might want to add something right here just below it that just takes that mass and multiplies it by 32.174. That's a pretty good estimate for gravity. And so that's the weight in pounds force. Notice we've got units over here. It's got to be in pounds force of the entire aircraft. And so that's 1.1013. And I usually round things to about 4 significant figures after the decimal here, because that we probably don't know it any more accurate than that. So that should be accurate enough. So there's the weight in pounds force, and then next to that, now we get to choose how much energy is used to launch this glider. And I have mine set at 4.5, and the reason I have that is because when I ran through my glider calculations, I decided I wanted to design this. My design speed was 16 feet per second roughly. And so previously I computed my launch velocity as a function of the kinetic energy. And of course we have an equation for that. So I chose this kinetic energy, 4.5, so that I would be launching very close to this design speed that I have. Okay, so my design speed is 16, and what I'm trying to launch at is 4.5 kinetic energy. So that's what I've got in there, and of course this is in feet pounds force. All right, so then we get into this section here where we need to fill out information about the airplane itself, and this includes both the aerodynamics and mass properties, or the inertia tensor here. So so the first thing is the reference lift coefficient, and this is the lift coefficient actually that we've trimmed our aircraft at. And so I trimmed mine at 0 degrees angle of attack to minimize drag on the fuselage. And so what we need to do here, actually I'm going to come back over here to mockup and just use fresh numbers for all of this. So I'm going to run this at 0 degrees angle of attack, and just simply click on update results here. And it tells me that this produces a lift coefficient at 0 degrees angle of attack of 0.6240. So that's the number that should go in right there. So 0.6240. Okay, and by the way, these coefficients, you can reorder these. If there's a better order that you would like to enter these in, you can rearrange it. This is one of the nice things about a JSON file, is that it's going to use a lookup table to find the numbers in here, and it's going to be looking for names of things. So I could move all of my inertias to the bottom, for example. Within this reference section, I can rearrange any of this information in here. So anyway, I'm just letting you know that that you might have a different way that you want to arrange this file if it makes more sense to you some other way. But you just need to keep all of the things inside of reference. All of these variables that are inside of there need to stay inside of reference. So okay, so the next thing here it's asking for is the inertia tensor. We're going to get that from our mass spreadsheet. So we'll come back over here. Here's my inertia calculator, my mass spreadsheet. And I'm going to scroll over here a little bit if I can. Let's see. Well, maybe I can come over here like this. It's not letting me go over. What's the problem? There we go. Okay, so this is my, we've got this inertia tensor labeled right here, and these are the values that correspond to each of these. So the first thing it's asking for here is IXX. So we come up here, IXX is in the top left corner, so it's the number right there. So it should be 0.0704. And like I said, I've changed a few things since I originally made this file over here. So I am really updating this to make sure it all matches. My IYY is this value right here, so that's 0.0478. And then IZZ is 0.11169. So I'm going to put in a 1117 to round it to 4 digits there. Okay, IXY is still 0, and that's because my aircraft is symmetric. Now yours may not be, so that may not be 0, but you can see these zeros here, these 4 zeros actually are the IXY and IYZ, so those are zeros. And then we've got these off diagonal terms here, the IXC. Now notice that this is a negative IXC, and this is just the way that this inertia tensor is defined. So we're asked for IXZ over here, and so if the negative of IXZ is minus 0.002, then the positive of IXZ should be positive 0.002, and that's a 0. So rounded to 4 digits. Okay, so this is in mine, this is a positive number, and that's because it's actually negative there, but the corresponding thing up here is negative. Now, you might notice that all of the off-diagonal terms up here are actually negative, and it's the diagonal terms that are positive. So you'll be entering in just, on the diagonal here, you copy those terms exactly, but any of the off-diagonal terms that you're using over in the spreadsheet, you'll need to flip the sign on, basically. So that's why I have a positive 0.002 over here. Okay, HX, HY, and HZ have to do with gyroscopic stuff on board the aircraft, like if we had a spinning motor or an engine or propeller, stuff like that. It's these gyroscopic effects. And so for our glider, we don't have any of those, so those are all 0. Okay, so now we get down to the rest of this is just aerodynamic information. The first 3 are the most difficult to get, and then after we get those 3, the rest of these just come straight out of mock-up, basically, except for the ones that we're going to assume are 0. So, okay, so CD0, CD1, and CD2. These are our 3 terms that describe our drag polar as a function of lift. So to get these, we need to run mock-up at 3 different angles of attack. So let's come over here to our spreadsheet, and what I'm going to do actually is I'm just going to start a new sheet. So I'm working on a fresh sheet here, and we need a minimum of 3 angles of attack. So I'm going to use, so this is my angle of attack alpha, and this is in degrees. I like to use something that's spaced out a little bit. So -5, 0, and 5 are probably pretty good. And that's good for us, or at least for this glider, because I've trimmed this at 0 degrees angle of attack. So hopefully it's going to be flying close to 0 most of the time. And so by capturing a few degrees on either side, I'm going to be able to capture the drag polar in this region pretty well. Okay, so what I need to do is I'm going to record the lift and the drag at each angle of attack. Okay, so let's come back over to mockup, and let's just run. Well, I already know it actually at 0 degrees angle of attack because I already ran it. So I'm getting 0.6240 and 0.0212. So I'm going to put in here 0.6240 and 0.0212. Okay, so that's make sure I got that right. So 0.6240 and 0.0212. So that's the lift and drag at 0 degrees angle of attack. Now I'm going to run -5 and update results. And now I'm getting, at that angle of attack, I'm getting -0.1613. And my drag, I'm getting 0.0102. Okay, and then I'm going to run this at 5 degrees angle of attack, +5. Update results. and there I'm getting 1.1003 and a drag of 0.0501. Okay, so these are the numbers straight out of mockup. Now there's one modification we need to make to this, and that's the fact that mockup doesn't include any drag for the fuselage here, for these cylinders that we added. So it doesn't have any way to account for that. So what we need to do is go into, and I had previously computed this. I walked through these in these glider calculations example. So what I have is a delta CD naught of 0.00343 for my fuselage drag. Okay, so I'm just going to take that 0.00343 and add it in over here. So my drag is really going to be equal to that plus 0.00343. And yes, you can autofill that. Let me just make sure I got that. 00343. Yeah. Okay, so now this is my true drag over here. This is my true drag coefficient. This is just the drag that came out of mockup. Okay, so I'm going to call this CD true. Okay, so now I need to fit what we were asked for over here is the three terms that describe the drag polar, or basically the drag as a function of lift. So I'm going to take the lift and the drag, the true drag. Let's see. So here's my lift, and here's the drag, and I'm going to insert a chart here. And so here's our chart, and I'm going to change this to, I like to look at these as a scatter plot so I can see my data points there. And then these data points, I'm actually going to fit a trend line to that, a polynomial, second order polynomial. So you can see that curve that goes through there, that second order polynomial, that's what we're looking for. And then I want to show the equation on the screen so I can see what the equation is for that. So this equation is actually tells me exactly what my drag terms are over here. Okay, so CD0 is just the term there that's not proportional to x squared or to x. So we've got some constant plus something proportional to x plus something proportional to x squared. And that x you can think of is our lift coefficient, because that's what we've used here on the x-axis is the lift coefficient. Okay, so we have some constant plus something times our lift coefficient plus something times the lift coefficient squared. Well, those three somethings are our three our terms here that describe that drag polar. So let's put that in here. So it's 0.0122 is CD naught. And then the next one here is minus 0.00311. Okay, so we've got an e to the minus 3 there, so that means we've got to move the decimal 3 places to the left. So that's going to put 2 zeros in front of the 3, and then we've got a 1, 1. So that's our CD1, and then the CD2 is 0.037. So there's our 0.037. Okay, so that was the hard stuff. The rest of this is really quite easy to get. We're just going to get it straight from mockup. Mockup does the rest of the aerodynamics for us, basically. So so let's just go down and get each of these terms. So we need derivatives with respect to alpha. That's what these comma alpha, or the comma a here, means with respect to alpha. So the change in lift with respect to alpha, change in rolling moment with respect to alpha, pitching moment, and yawing moment. Well, since my aircraft is perfectly symmetric, the change in rolling moment with respect to alpha and the change in yawing moment with respect to alpha are both exactly 0. Now yours may not be, and I'm going to show you where to get that if they are non-zero. But if your aircraft is symmetric, then those should be exactly 0, and you shouldn't need to worry about this. So, but let's just get these derivatives with respect to alpha in general. So we're going to go to performance derivatives, and we want to run this at angle of attack of 0, because we want the information as close to our trim point as possible. So angle of attack of 0, performance derivatives, I'm going to update results. And here we go. Here are the numbers that we need. So the change in lift with respect to alpha is 5.2636. So that's what I'm going to put in right here, 5.2636. Okay, so Again, my next one is 0 because I have a symmetric symmetric aircraft. And then change in pitching moment with respect to alpha is right here, so it's a minus 1.2111. Okay, so we've got that. So let me just show you where to get derivatives with respect to alpha. If you're these other two derivatives here, if your aircraft is not symmetric, then those are probably not 0 for you. Okay, so so they're not going to show up here. These are the most common derivatives that are shown right here. So let's click on Save Results instead, and Save Results will pop up this file, and I'm just going to take, it says, what do you want to call this file? And I just took the default file name, which is kind of long. I'm going to click on it and open it, and yours is going to open in some text editor. You know, I'm using Visual Studio Code just because I like the way that it colors things, and I like the dark background and stuff like that I can set. So, but yours might open in a text editor, whatever. This is just a huge JSON file that has a whole bunch of information in it. And the first thing that it shows us is derivatives with respect to alpha. And this is derivatives with respect to angle in radians. So that's exactly what we need. That's what our derivatives over here are all with respect to radians in the denominator. Okay, so that's fine. So what we want to know, at first it's going to show us derivatives with respect to alpha for wing 1 right, and then for wing 1 left, and then for h stab right and h stab left. Well, I don't care about any of those. In this editor, I can click on this little down arrow and it will collapse that pocket of information. See, that's what's kind of cool about these JSON files. See, this is a pocket of information that all pertains to wing 1 left. And I can collapse that to turn it off, but you don't need to. You can just scroll down if you want to. So I'm just going to collapse these because I'm not interested in that. What I'm interested in is this pocket of information here, right? So this is the derivatives with respect to alpha for the entire aircraft, not for each of the components, but for the entire aircraft. So what I'm looking for here, well, let's look at the first derivative with respect to alpha that we wanted was the lift coefficient with respect to alpha. So that's this number right here. So you can see this is the number that was copied over here. This is 5.2636. That's exactly what we have right there. So that's the change in lift with respect to alpha on the entire aircraft. Well, you may, let me come back over to this file here. What we are looking for here is the change in rolling moment with respect to alpha, which it didn't show over here because that's kind of an odd thing. It's if your aircraft is not symmetric, but we can get it out of here if we go right here. So this is the rolling moment. So you can see that my rolling moment, the change in rolling moment with respect to alpha, is some number times e to the minus 15. So anytime you see an e to the minus 15 or an e to the minus 16, that tells you that this is essentially 0 to the computer. The computer can only compute things to a certain amount of precision, and using modern computers, most of those computations are what we call double precision. That means that they can estimate it to this value of e to the minus 16. So when you see e to the minus 16 out here, what it means is this number is basically 0 to the computer. It can't discern that, and the difference between that and 0, basically. That's within the error that the computer knows things. So let's come back over here. We were looking for the rolling moment or the yawing moment with respect to alpha. Well, for me, both of those are exactly 0. Here's my yawing moment with respect to alpha. Here's my rolling moment with respect to alpha. Those are both exactly 0 because I have a symmetric aircraft, okay? But again, yours might not be if your aircraft is not symmetric. Okay, so let's keep going down here. These next derivatives we're actually going to drop and not worry about those. They're a little tricky to get, and mockup is not capable of estimating these derivatives. These derivatives are usually I would say kind of secondary in importance. They have to do with the acceleration of the aircraft and the time it takes for the vorticity from the main wing to travel downwind and hit your tail. So it has to do with things like that are a little bit tricky to get, and you can get them from CFD or wind tunnel testing, or there are also estimates for these things that you can get out of textbooks, but we're going to say that they're 0. They're usually, at least for us, we're going to say that they have a minor effect, which I think is pretty true. They don't have much of an effect for us. Okay, so then let's go down to this next set of derivatives here. These are changes with respect to what this calls b, or what mockup calls beta, okay? So the next thing here is cy comma beta. So that's that value here. So we need a minus 0.4544 right there. CL beta, so that's a change in rolling moment with respect to beta, so minus 1981. And then let's see, CM beta. So this is a change in my pitching moment with respect to beta. And again, this is probably 0 for symmetric aircraft. So that's why I've got a 0 there, but yours may not be symmetric. So let's just go and find that in here. So this is what I'm looking for, is a derivative with respect to beta, right? So let's now collapse this derivatives with respect to alpha in general. And we see the next set of data is derivatives with respect to beta. And again, I don't care about the individual derivatives for the components. What I care about is the change on my entire aircraft with respect to beta. So what we're looking for is Cm comma beta. That's my pitching moment with respect to beta. And you can see, again, that's a very, very small number. E to the minus 14, again, that is really, really close to machine precision. In fact, e to the minus 13, anything that's actually below e to the minus 12, I would consider 0 to machine precision. So all of these numbers here, and e to the minus 14 is, I would consider that 0, okay? So that is, so we don't need to worry about that, Cm beta, and then Cn beta, so that's a change in yawing moment with respect to beta, and that's 0.0515. So let's put that in there, 515. Okay, and then now we need changes with respect to P, Q, and R. And these are down in these damping derivatives. So we've got CY P bar. Now, again, over in this file, it's kind of truncating this a little bit. This actually is with respect to P bar. This is a non-dimensional rolling moment, okay? Non-dimensional pitching moment here is Q bar, and non-dimensional yawing moment is R bar, but that's exactly what these are looking for. P, Q, and R, all in non-dimensional form. So CY comma P is minus, I'm just pulling that from right here, the minus 0.4507. And then we can just go down here. CL comma P is minus 0.6228. CN comma P is minus 0.0489. CLQ bar is 2.4062. And then we've got CDQ bar 0.0831. And then CMQ bar is minus 9.9793. CYR bar is 0.3480. CLR bar is 0.2676. And then CNR bar is minus 0.0474. Okay, and that's it. We've now, so I'm gonna just save this. So I've now updated this, and I'm gonna get rid of this other file that I just used to get the derivatives. But anyway, so this is the final file now. This JSON file that I can now submit for the fly-off. And so that's the JSON file that you'll submit now, that now represents all of the mass and all of the aerodynamic properties that are going to be used here in the simulator to estimate the performance of this glider in its flight.